So now we're moving into chapter 28, which is the beginning of magnetic fields. Now we're going to kind of treat this the same way as we did when we first started dealing with electric fields, which is kind of a basic understanding of what those fields are doing, and then moving into the more complicated algebra. Okay, so the first chapter, pretty straightforward, not a whole lot to really consider. Okay, you've probably heard the term magnetic field before. Okay, now there's something you need to know about magnetic fields. We don't really know what creates them, and we don't really know why they're created. We know that magnetic fields come from one of two different things. Two different things lead to magnetic fields. The first is a current carrying wire. A current carrying wire can induce a magnetic field. Now, this is one of the reasons why when they first started putting up power lines all over the country, those big steel constructions that had the power lines running in between them, people got really nervous because those power lines were creating magnetic fields. Thankfully, we found that magnetic fields, for the most part, are very harmless to an individual. Okay? So a current carrying wire can induce a magnetic field. We're not going to talk about this too much. That's going to come up in the next couple chapters, okay? And you're going to see why in a second. The other way that we produce a magnetic field is that it's an intrinsic quality of a material. An intrinsic quality of material. Remember that we said that charge was kind of an intrinsic quality of different types of materials. So this material has some kind of positive charge, this kind of material has some kind of negative charge. Same thing with magnetic fields. It is most of the time just a property of the material. This material produces a magnetic field because it has a north pole and a south pole. Okay? Here's where it starts getting really nasty. Okay? Moving particles create a magnetic field. We see that with the first thing right there. So a current carrying wire, we are going to produce a magnetic field. Magnetic fields also change the trajectory of moving particles. So you can see where this relationship is going to begin to form. So a moving particle induces a magnetic field, and magnetic fields do different things to a moving particle. So yeah, it's going to get kind of weird, and we're going to be talking a lot of, well, A does this to B, but B also does this to A. As long as you keep your thought process straightforward, it really isn't too bad, but it can get complicated a little bit the first couple times you deal with it. Okay, so the first thing we want to do is we want to analyze the definition of B. B stands for the magnetic field. It should be intuitively obvious why they chose the variable B. Can't choose M. We use M for too much. So B stands for the magnetic field. And the first way that all these physicists started to analyze the magnetic field was by firing charged particles through the magnetic field. Okay? And what they found was that those moving particles from the magnetic field will feel a force. So there is an induced force onto these particles as they are shot through a field, a magnetic field. Okay? Now the force that these particles feel, FB, the force from the magnetic field on these particles, is equal to Q, the charge on the particle, multiplied by V cross B. V stands for the velocity of the particle, B stands for the magnetic field. Notice that the magnetic field is a vector quantity, so the direction matters. So the direction of the particle's travel, V, is also going to impact, along with B, the force that this object feels. Okay? Now, a couple of important things here. First off, this Q here is hugely important. The sign on the charge does matter. Remember how sometimes they would trip you up by saying, what's the force that this particle feels, and they would give you a negative charge? You need to be very, very careful with the minus signs on these charges. That will impact the direction of your force from the magnetic field. Okay? Now, notice that because we're doing a cross product here, FB, the force from the magnetic field, is perpendicular to V and B. That's the definition of our cross product. The resulting vector quantity is perpendicular to the first two vectors that are used to find the cross product. Okay? There's another thing. VB cannot change the magnitude of V. The magnitude of V cannot change. So all you can do is change the direction that the particle is traveling, because the particle is going to feel a force, okay? So you should start thinking about centripetal forces right now. The particle will feel a force, so the trajectory of the particle will change. However, the velocity, the magnitude of the velocity will not change. The direction changes, but the magnitude of the velocity does not change. What that means is that there is no change in kinetic energy. No change in kinetic energy. Now, if there's no change in the kinetic energy, then this is the big leap. This is the big leap in logic. Magnetic fields cannot do work. Go back to last year, okay, I'm sure you guys all remember. We said that work done changed the kinetic energy of our object. If we cannot change the kinetic energy of our object because we cannot change the magnitude of V, what that means is that magnetic field cannot do any work, okay? That is hugely important. Let's go into the actual unit analysis here for the magnetic field. I'll come back over here and do the unit analysis. The unit that we will be using for the magnetic field is the Tesla. So 1 Tesla, or 1 big T for Tesla, is equal to a Newton per Coulomb meter per second. Okay? Newton, Coulomb, meter per second down there in the denominator. Okay? And now what that also means is, remember that a Coulomb per second is the same thing as an amp. A Coulomb per second is the same thing as an amp. So what that also means is that the Tesla is equal to a Newton per amp times a meter. A Newton per amp times a meter. Lastly, there was an old unit for magnetic fields that isn't really used very often anymore. I had to use it for my magnetic field research in grad school, and we can talk about that when I get back from vacation. We know that 1 Tesla is equal to 10 to the 4th Gauss. This is the old unit for the magnetic field. That's called a Gauss, and we have 10 to the 4th Gauss in 1 Tesla. Okay, that's the old unit for magnetic fields. Okay? Now you guys probably know also about the magnetic field lines. Okay? If we kind of go to Looney Tunes here a little bit, so we're talking like Daffy Duck, Bugs Bunny, they always have a magnet that looks something like this. And that magnet has a north side and a south side. Okay? So magnets have poles. There is a north pole and there is a south pole. We have never experienced a magnetic monopole. We have never found in nature a magnet that only consists of a north or a south pole. Okay? We say that the magnetic field lines flow from north to south. Okay, that's our convention that we're going to use. Okay? Remember that opposites attract the same way as what we're talking about with positive charges and negative charges. Positive and negative attract each other, north and south attract each other, north and north repel, the same way that positive and positive also repel. Okay? Now if I were to break this thing, if I were to come in here and try to break this magnet, I then form a new magnet. So if I came in here and broke it into 2 pieces, I'm a wonderful artist, you all know that at this point. I don't know why this one ended up more square than that one, but just go with me here, okay? If we try to break this, then we just form a new north and south pole. So now I have a north and a south here, and a north and a south here. No matter how many times I break the magnet, I'm always going to end up with a north and a south pole. We will not experience a magnetic monopole. Okay? Now I want you guys to do a little bit of reading here. It's not going to be too hugely important for the AP test or for your test. But I do want you guys to do a little bit of reading here. So read 28.4 and 28.5. Read those 2 sections. Again, it's kind of more of a basic understanding of magnets. It's not going to come up on the AP that much, but it's really good reading, and those of you that are really interested in learning more about this stuff, Mert and Andy, feel free to go ahead and read this stuff. It's really, really cool, okay? So now we're going to move on into the next part of magnetic fields.